A high-speed train can carry hundreds of tons and run along the rails at over 300 kilometers per hour. But for this to happen safely, there's a part that needs to be almost perfect: the rail. It looks like just a steel bar, but it's actually a gigantic structure, manufactured with millimeter precision, capable of withstanding heat, impact, extreme weight, and decades of use. A single mistake, a small crack, or an almost invisible deformation could put thousands of lives at risk. But how does iron ore turn into rails over 100 meters long? And how are these huge bars transported, installed, and joined together to form kilometers of railway? That's what you're going to see now. High-speed railways carry trains that reach the impressive speed of 300 to 350 kilometers per hour, which is equivalent to the speed of a Formula One car during a race. But unlike a race car that weighs about 800 kilograms, a train weighs hundreds of tons. Conventional tracks wouldn't be able to withstand the extreme stresses of high-speed trains. The main problem lies in the welded joints and very sharp curves. On a regular track, every time the train passes over a joint, there's an impact and that rattling sound occurs. At 300 kilometers per hour, these small bumps would turn into hammer blows, capable of disintegrating the structure and derailing the train. To ensure a smooth and safe journey, the key is to eliminate the joints and design extremely gentle curves. This requires manufacturing rail sections longer than a football field. But how do you make such a large piece of steel? The story of these rails begins deep in the Austrian Alps. Among houses that look like they're made of chocolate and snow-covered mountains, the Bustalpen plant is hidden away, the world leader in the manufacture of giant rails. The process is a visual spectacle. First, iron ore, coke, and limestone are placed in a blast furnace. An intense electric current heats the inside of the furnace to about 1,650 degrees. When it reaches this temperature, the metal becomes almost liquid, and the impurities float to the surface, where they are removed. Then the metal flows into a large ladle, where carbon, manganese, and other elements are added to increase its durability. This alloy goes down through a ceramic tube, which protects it from exposure to oxygen, something that could ruin the metal. From there, the molten metal goes to molds that turn it into continuous rectangular blocks, called slabs. Acetylene torches cut each slab into 12-foot lengths. Acetylene torches cut each slab into 12-centimeter lengths. Next, an overhead crane moves these blocks to a furnace, where, over the next 7 hours, they are reheated to about 1,200 to 1,260 degrees Celsius to soften the steel. Every 5 minutes, a new glowing bar comes out of the furnace. When they leave the furnace, the bars are sprayed with high-pressure water jets. The pressure is so great that, when it comes into contact with the extreme heat, the water literally explodes. This expansive force removes any residue, leaving the surface spotless. After being cleaned, the slabs go to a workshop where huge steel cylinders, called rollers, work like an industrial pasta machine. With millimeter precision, these rollers stretch the metal until it reaches 120 meters in length. They press the steel repeatedly, stretching the piece and giving it the famous T shape. Right after coming out of the last roller, while it's still hot, the rail goes through a cooling system controlled by a computer. Although the rail already has its final shape, the top part, where the wheel rests, is still too soft. To harden it, the rails are dipped in a liquid plastic called polymer. This cooling process makes the steel's molecular structure much denser than it would be if it were cooled in the open air. By hardening the railhead, it allows the train wheels to slide over the surface, minimizing friction and wear. This not only makes the train faster, but also allows the track to last up to 25 years under heavy use. When the rail comes out of the hardening process, it still isn't perfectly straight. To fix this, it is placed in a straightening machine. The rail passes through 2 sets of large diameter rollers. The first group presses the steel vertically, up and down, while the second makes the correction horizontally from side to side. The machine bends the rail beyond its natural spring-back point, forcing the steel fibers to realign. It's a delicate balance. If the pressure is too low, the rail returns to its original curve. If the pressure is too great, the steel weakens. Laser sensors measure the deviation and automatically adjust the pressure of the rollers. When the rail is perfectly straight, it's time to give its final dimensions. The ends usually have small deformations caused by the rail entering and leaving the rolling mill rollers. These parts are cut with large diameter circular saws cooled by water. The cut needs to be perfectly perpendicular so that, when it is welded onto the track, there are no empty gaps. Before leaving the factory, each rail goes through a complete inspection at a speed of 1.5 meters per second. A system of cameras and lasers detects any imperfection. The tolerance is measured in tenths of a millimeter. If the head of the rail is even a millimeter wider than it should be, the wear on the train wheels will be uneven. Magnetic tests detect microscopic cracks and fatigue on the steel surface through changes in electromagnetic fields, ensuring that there are no fissures that could expand. Ultrasonic rays emit sound waves that pass through the steel to locate air bubbles, impurities, or internal microfractures invisible to the human eye. If the computer detects the slightest flaw, the rail is sent for manual inspection. If there is an internal defect, it is immediately rejected. The lives of thousands of passengers depend on there not being a single scratch. The final challenge is transportation. How do you transport a bar that's 120 meters long and weighs 7 tons? For this, robotic arms equipped with giant electromagnets are used, lifting the rails with impressive delicacy. They are placed on ultra-long wagons, separated by just a few centimeters, and protected by shock absorbers and wedges so they don't touch each other. A single scratch during the journey could weaken the steel and force it to be returned to the furnace. But how are the train tracks assembled? To lay the tracks, what is known as an integral renewal train is used. It's basically a factory on wheels, hundreds of meters long, capable of doing all the work. These machines can install between 500 and 2,000 meters of track per day, something that used to require weeks of work and hundreds of workers. The machine moves forward over the ballast. Hydraulic arms position the new rails, each 120 meters long, which were transported in special wagons. It's the most spectacular part of the process. The machine has a storage area for concrete sleepers that move along a conveyor belt. As the machine moves forward, rollers guide the heavy steel rails and gently place them onto the support plates of the sleepers. Immediately after the rail touches the sleeper, a unit of the machine detects the fasteners and applies a rotational force to tighten the clamps. This leaves the rail secured, but with the necessary flexibility to absorb the expansions caused by heat. After the track is assembled, the tamping machine comes into action. This machine has metal fingers that penetrate the ballast and vibrate. This makes the stones settle perfectly under the sleepers, leveling the track and giving the exact tilt on the curves, so that high-speed trains can travel at over 300 km/h without constant and noisy vibration. The rails are not simply bolted to each other. They are turned into a single continuous piece, kilometers long through welding. A ceramic mold is placed around the joint between two rails, leaving a small gap between them. In a crucible positioned above the mold, a mixture of aluminum powder and iron oxide is combined. The mixture is ignited and a chemical reaction occurs that reaches 2,500 degrees Celsius in a few seconds. The molten steel falls into the mold, filling the empty space and fusing the ends of the rails. After it cools, the mold is broken and a grinding machine polishes the surface until the joint becomes completely imperceptible to the touch. That's how train rails are joined, and that was today's video. Don't forget to leave a like and subscribe to the channel.